All right, so convergent is when the limit of your summation or your series exists. Divergent is when the limit does not exist for it. So if we were looking back at activity 1, this is our general series. So if I said limit as n goes to infinity of 2 to the nth power minus 1 over 2 to the nth, if I want to look at this and say, does it converge or does it diverge? Well, in the long run, do we care about this negative 1 when we're looking at infinity? Nope. We can drop it. So this limit, the limit's the same. The expressions are totally different. They are not equal, but the limits are the same. So I can drop the negative 1. Now, 2 to the n divided by 2 to the n will always equal 1. So, can you see that as I shade more and more of this in, I'm getting closer and closer to 1. So my limit is 1, because I'll never go over 1. Everything's going to be stuck within this box. Now, I may or may have to go to infinity to even try to approach 1, because even at 10, I'm still not at 1. So it will be impossible to get to 1, but I will be approaching 1. That is the limit. So this will be called convergent. I am approaching a single number. My sum of this whole thing should equal 1 if I could go to infinity. All right. And then rational numbers. I wanted to go over this before doing the side example on 543 on the bottom. I don't know if you've seen this before. I had never seen it before, but when I was student teaching, I saw this. So fart. So fractions and repeating decimals and terminating decimals are rational numbers. We typically just shorthand it and say fractions, but those actually are repeating decimals. So for example, if I have 1/9, that's the repeating decimal of 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. You get the idea, okay? One more dot. Or if I had said 1/4 as a fraction, that's a terminating decimal. So if you ever see a repeating decimal or a terminating decimal, you know that you can write that also as a fraction because they are all rational. If you see pi, for example, there's no pattern. The square root of 2, there's no pattern. Those aren't rational, they are irrational because they don't repeat and they don't terminate. Terminate just means end and stop. They are decimals. You can write them as decimals, but they're not repeating and not terminating. So the mini example on the bottom of 543 is to take 7/9, which I just told you is a decimal, is 0.777777. You get the idea. You can write this as fractions, because this place value is 7/10. This place value is 7/100. Ignoring the previous one. This one is 7/1000. This one is 7/10,000. And so on and so on and so forth. So, is this automatically a fraction? We don't think of it as a fraction. We think of this as a fraction, but do we think of either of these as being a sequence? No. Or a summation or series? No. But they are, because if I take all of these numbers together, they're going to make this decimal, which will make that fraction. These are all equivalent. So, is this a geometric or arithmetic series? Because it's adding, so it's series. Geometric, because if I take this term divided by that term, I'm going to get a common ratio of, so let's see, if I have 7/100, I'm going to divide it by 7/10. I'm going to have 7/100 multiplied by the reciprocal, 10/7. 7s make 1s. 10 divided by 100 is 1/10. So my common ratio here is 1/10, and the first term is 7/10. So we're going to see what we can do with that information, but just wanted to put this in context of series and of something you've seen before. And it's a cool fact, you can break up decimals because decimals are just fractions. That's why we call this place value tenths, hundredths, thousandths. They're all fractions. All right, now moving on to example 1. So, I guess that's another question too. We can go back and do this, then I'll pause this video. All right, so back over here, if I want to look at this series, what is a grand pattern or general pattern I can use to write this series? Pause it, figure it out, and come back. All right, so this series, because I am adding, I'm going to start at n equals 1, and we're just going to go to infinity because this 7, they keep going for forever. My first term is 7/10. My common ratio is 10, and n minus 1 then goes up in my exponent. So, random comment of, yeah, you can do that. Does this converge or diverge? Think about it, and then we'll come back and see where it's going to go. I can't go too far. All right, we'll do example 1, then example 1, and then I'll mention activity 2, and then we'll go on. So example 1, consider the infinite sequence that's been given. It's associated with its series, meaning you just add all the numbers up. What type of sequence is this? So we have 4/3 added to 8/3 added to 16/3, and our general pattern is 2 to the n plus 1 over 3. And this continues for forever. Okay, so this is the series because we're adding the numbers up. A sequence would just be putting these with commas. What type of sequence is this? So 1, is there a common difference? Is there a common ratio if I divide? Or neither? Pause, figure it out. It's geometric. So this will be a geometric 1 because we have a common ratio. And the common ratio in this case is going to be 2. As you can see, 4 times 2, 8 times 2, 16 times 2. We'll get to the next one. Our base here is 2. And the first 5 partial sums. So this is the first partial sum. Is 4/3. The second partial sum will be adding 4/3 with 8/3, so that's 12/3. But we can simplify that to 4. And I want you to continue and then check with the book. What is S sub 3, S sub 4, S sub 5? And then pause it, do that, come back. Does it seem to converge? And I want to read what the book says. The sequence of partial sums appears to increase without a limit, so the infinite series does not converge. This number just keeps getting bigger. It's not getting closer to anything. The differences between these are not getting smaller. It's not approaching or crawling towards a number. It's pretty much just keep going and keep increasing and keep getting bigger, which makes sense because my denominator is not changing. The numerator gets bigger every single time, but my denominator is not keeping pace with it to help make it a smaller fraction. All right, activity 2. If you know how to do Excel, it'd be an awesome thing to do, but I'm not going to make you figure out how to do it. And our calculators can do it. It's just a funky way of doing it, and I haven't found a great tutorial for it. So you can read it, try it on your own as much as you can. Skip number 5 on the homework. Skip number 5. Number 5 is similar to this and wants you to use Excel or another calculator program that I'm not going to go into the detail for because it doesn't matter as much to get everyone on the same page with it. It's interesting because you can just see how the numbers go, but you can also do it by hand. Excel is just nice because it does it for you quickly. But skip number 5 on your homework. Do not do it unless you want to try it. Go for it. But it's similar to activity 2. All right, so I'm going to stop this video, and then I will start in on the infinite geometric series part.